Good afternoon. My name is Erdei from Bézi Research Institute from Hungary. In my presentation, I will describe the possibilities that are now available for the life cycle analysis of a structure, and I will mainly focus on the development of non-destructive testing method through modeling. The failure of a pressure vessel can lead to emergencies, and therefore the causes and possibilities of their occurrence need to be investigated, for which the development of the science is providing more and more possibilities. Potential failures can occur during the design, the manufacture and the operation, and are mainly caused by the stored medium, the ambient atmosphere, the operating pressure and temperature, and the cyclical operation. Fractures always occur as a crack develops and then propagates. The initiation and propagation speed of the crack must be investigated. Mechanical analysis can be done analytically, but finite element analysis of a pressure vessel can make complex calculation easier. This work demonstrates how we can support analytical calculation with numerical modeling, thereby reducing the computational requirements and time. A high percentage of failure are caused by cracking defects, which mainly occur around weld and at critical points of the structure. These critical points can also be determined from the finite element simulation to identify the location of the crack initiation, which should be able to detect it by non-destructive testing techniques. An industrial example will be used to illustrate this method. The object of the investigation is a 10 meter high ammonia container with a wall thickness of 100 millimeter, which has been in operation for almost 50 years. Due to the changes in technology, the frequency of internal inspection had to be reduced and periodical external inspection had to be added, so that the following calculation had to be done. To make an improvement in the assessment, we need to know the current state of the vessel and its history. Having obtained a general view of the current state of the vessel, finite element software is used to map the stress field, which can be used to identify the critical damage location. The finite element calculations were performed in MSCMark software. It is also necessary to determine whether the discontinuity in the structure are acceptable and how their increase affects the safety, for which various analytical calculations are available, for example, R6 method or failure assessment diagram, and in various standards and specifications such as FitNet or SynTap and so on. For the calculation of these, we use the VERB 7.0 software. Once a critical test location and critical crack sizes in the structure that you want to detect during the inspection have been identified, you need to determine which inspection technique you want to use. In this case, phasor rigorous ultrasonic testing was used, and further calculation need to be done to determine the setups that can be used to guarantee that the critical defects can be detected at the critical locations. For this purpose, we use a semi-analytical software called SIVA which allows non-destructive testing modeling, parametrical calculations, and probability of detection curves, which were used in our work. Over the years, the container has been tested by visually, by external and internal penetration testing and hardness testing, and ultrasonic testing, and no surface or internal discontinuity have been found during the operation. The modification was motivated by the change in the operation condition to reduce the frequency of the internal inspection and to inspect the vessel from the outside in this location, which required a technique capable of mapping the full cross-section. In addition, the wall thickness of 100 millimeter could also be a reason for the difficulty of this inspection. For the above reasons, ultrasonic testing is suitable for this task, but it needs to be investigated and improvements to the technique are proposed. So further calculation need to be carried out. To determine what test setup is required, we need to determine what the error range is that should already be detected by sufficient confidence under the given conditions. This requires fracture mechanics calculation to be carried out, which requires a prior knowledge of the stress distribution in the structure and the critical test location, for which finite element calculation have been performed. The finite element calculation were used to investigate the stress distribution in the wall, the end elements, and the vinicity of the cutouts due to the internal pressure, the self-weight, and the temperature. In order to simplify the calculation, axisymmetric models were created for the wall and the end elements, and 3D calculation was performed for the vinicity of the cutouts. The resulting von Wiese's stress distribution in the wall is shown in the pictures. The stress distribution was used for the fracture mechanics calculation, and the stress peaks, which was obtained from the simulation, were used to deduce the critical location that should be tested. The critical location obtained by the simulation are the same as those specified by the manufacturer, which is the weld in the full cross-section at the high stress values at the bottom and the cover part and the surroundings of the cuttings. The next step was to determine the critical crack sizes. Any crack detected during the test shall be assessed to determine whether it compromises the integrity of the structure and whether it is likely to reach this state within the test period. For this reason, fracture mechanics calculations were performed where the crack size associated with failure and the propagation of the crack size were determined. The critical crack sizes were determined using the two-parameter safety diagram called FAD, Failure Assessment Diagram, which based on FitNet, and we use the web software to determine it. The types of cracks investigated are axial and circumferential, pro-wall, internal surface, and extensive cracks. The failure assessment diagram methodology replaces the free fracture mechanics parameters relationship, the fracture softness, the defect size, and the loading by two parameters in order to have a plane presentation representation where non-dimensional crack driving force KR and non-dimensional applied stress LR are the coordinates. The non-dimensional crack driving force is defined as the ratio of the applied stress intensity factor and the fracture softness of the material. The non-dimensional stress is described as the ratio of the stress caused by the cracks and the loadings and the yield stress. When a growing crack reaches the failure assessment curve, fracture occurs. The software used makes it very quick and easy to determine these fracture crack sizes. You just have to select the fracture mechanics calculation you want to perform, then enter the geometry and loading data, and the program calculates the crack sizes for the different fracture cases. For example, circumferential crack with a height of 30.5 millimeter can be considered as dangerous. The Siva software used for this task is capable to calculating a number of non-destructive tests, such as ultrasonic, eddy current, and so on. In the software, the ultrasonic test design was prepared, simulating the weld inspection using a built-in geometry and a phase array technique. The modeling also determined the appropriate range of the sectorial scan, the number of elements to be vibrated, and the appropriate index offset for which a parametric study was made to determine the index offset where the maximum echo come from the given defect in the weld route. The software can also be used to carry out sensitivity tests where the effect of several parameters can be tested side by side to determine, for example, the best and the worst case, the effect of the parameter on each other, and the percentage of the output signal that each parameter affects. From the results of the sensitivity test, it is now easy to calculate probability of detection curves, so-called POD curves, where the POD curve can be calculated from the line fitted to the data point with statistical methods. And from the POD curve, we can obtain the crack size that is 90% of detectable, 90% detectable at the 95% confidence level, and this is the typical value of the NDT. With our parameters and settings, the testing technique can detect cracks up to 4.7 millimeter. Thus, it can be concluded that the testing technique is suitable for this task. To summarizing this, from the FEM simulation, we can determine the critical location and the stress field. The stress field was used for the FAT diagram, where we can determine the critical crack sizes that could be detected with the the non-destructive testing. We use a ultrasonic testing method, and we modeled it in the SIVA software, where we can determine the optional test setups to detect discontinuity with a high safety level. To conclude this, that we can see that the application of these analytical, semi-analytical, numerical methods and software can provide increased safety. Thank you for your attention.